In video 20b, we talk about the effect of mechanical force on energy landscapes of bonds. We address concepts, definitions, and equations. So, addressing the molecular basis of material properties, we consider the fact that materials are made up of molecular bonds. One question we ask is, how does the force applied to these bonds relate to the length of the bonds? And to answer this, we have to consider the energy landscapes of a bond. You may have seen energy landscapes like this in chemistry, often where we talk about the energy of the bond in regards to some reaction coordinate, but in this case where the reaction coordinate is specifically the length of the bond. The other questions we ask here are, how does the stress on the material translate to the force on the bonds, and how does the strain in the material translate to bond length? To answer these, we would need to consider the nanostructure of the material. Our key concept for understanding molecular mechanics, that is, the molecular basis of the mechanics of material, is to understand energy landscapes. We define the bond energy function, U sub r, to be the energy of the bond at a length r. That is, this U is just a plot of the energy as a function of bond length. And that's what we refer to as an energy landscape. We call R naught to be the equilibrium bond length, where the energy is minimum. We call U naught, or the energy at R naught, the energy at the equilibrium bond length, to be the equilibrium bond energy, and that's the value of the energy at that minimum. That is, it's the minimum of the energy. We define the force F applied to the bond using the deformation sign convention, so the force is greater than 0 when the bond is under tension. We see that the force to hold the bond R is the derivative then of the energy function, and we show that in this plot here. So we saw that the force to hold the bond at a length R is the derivative of the energy function. And now let's look at a few more things. By definition of the local minimum, the energy must be greater than the equilibrium energy for R near R naught. That is, if we're near R naught, all of these energies are greater than U naught, which is just to say that that U naught was a minimum. So when R is less than R naught, the force is 0 because the energy is dropping to that equilibrium bond energy. That is, the force or the slope of the energy function is less than 0 for R is less than R naught. On the other hand, when R is greater than R naught, what we see is, because the energy must increase as we go away, the force is positive, and so that force is greater than 0 in this region. Finally, if the force is at 0, of course, the derivative at a local minimum is 0, so the force is 0 right at that point at R naught. That is, no force is needed to keep the bonds at equilibrium. Our next concept is bond spring constants. So when R is near R naught, when the length of the bond is close to the equilibrium length, the second order Taylor expansion approximates the energy function. That is, we can approximate any function as the value of that function at a nearby point plus the difference between those points times the slope at that point, plus 1/2 the difference squared times the second derivative, etc. So this is the Taylor expansion. You might remember this from calculus. This is actually one of the most useful things we do. Oh, we can use this for all sorts of stuff. So remember it if you haven't already. So in this case, we want the second order Taylor expansion, meaning just up through the second derivative. We will define the bond stiffness as the second derivative at the equilibrium bond length. And we'll see why that is in a moment. So recall that the derivative of the energy the derivative of the energy, which is equal to the force at the equilibrium bond length, is 0. And that the bond energy at the equilibrium bond length is the equilibrium energy. And so if we exchange these out into the first function, we had said that the energy at R, we bring that over, is equal to the energy at R naught, which we could have called U naught. And then this term up here, that's 0, so that cancels out. And then this term here, we have the 1/2. We replace this with K, and then we keep the R minus R naught squared. And so that results in this equation that is that the energy is equal to the equilibrium bond energy plus a spring-like function. And so that says whatever the bond looked like totally, it approximates this with that R naught, that U naught, and then the spring telling you the steepness of this. And this is just to say that within the linear range, the spring constant of the bond is the second order. Of course, outside the linear range, it will deviate from this spring-like perfect behavior. So we'll now look at an example of an energy landscape. So we'll ask, what is the equilibrium length? So we recall the equilibrium length was R naught. What's the equilibrium energy? That was the U naught, which is the energy at R naught. And the spring constant of a bond. Recall the spring constant was the second derivative of the energy with respect to R, again calculated at R naught. So we're asked, what are those things? So this is simply mathematical manipulation given a specific bond energy function. And in this case, we're given this energy function here. And we can see down here where this is plotted. And so we can see, and we're plotting here, R divided by this D is a parameter of the bond, and U divided by this C. So in this energy function, C has units of energy and D has units of length. So our solution to this is, first we need to consider, we've had the energy, and we see for a number of these things we need to calculate up to second derivative. So first we'll take the derivative, and so this is an exponent. You keep the exponent, you put the cofactor in front. Whoops, I left out a little c here. The cofactor in front that is multiplying by the derivative of what's inside the exponent. And then the same thing here for the second term. Then we take the derivative again, and we again multiply by negative 2 over d, so we get 4c over d squared. We do the same thing in the other term, and so we now have our derivatives. And now we start using our definitions. The equilibrium bond length, we are asked to calculate R naught, and we didn't have R naught if you noticed here, but we know it occurs where the derivative is 0. So we just take that derivative, we set it to 0. And we'll call the value we're taking it at R naught because that's what we're trying to find. So we will plug in R naught here and here into our function for the derivative up here. And then we simplify. And so we'll set these two equal to each other from what we had above. And then we will knock out the 1 over d, and we'll also combine the two exponents here. So the exponent here of negative r over d, when we divide that by this area here, it's simply subtracting this argument inside from the argument there. That's a property of exponents. And so that leaves us with 2 equals the exponent of r over d. And then if we take the natural log of both sides, we have natural log of 2 is r over d, or r naught equals 2 times the natural log of d. We'll find both of these as useful terms here. Continuing this example, we found the equilibrium bond length, but we still need to find the equilibrium bond energy and the spring constant. The equilibrium bond energy is equal to the energy function calculated at r naught, which is this expression here copied over from the previous values, and the spring constant is the second derivative evaluated at r naught. And keeping in mind that we calculated this value for r naught, and because r naught always shows up in a ratio with over d, it may be more useful to remember it in this term. And in fact, we can start because we keep having these expressions, exponent of minus 2 r naught over d, when we plug in this value, gets the value 1/4, whereas exponent of minus r over d gives us the value 1/2. And so we can use that to exchange in that the equilibrium bond length is simply c, this cofactor c, divided times 1/4 minus c to over 2, which is just minus c over 4. Now the spring constant is, again, we have this, the expression we calculated before. We exchange in this to be 1/4, exchange in this to be 1/2, and we see that we have 4c over d squared divided by 4. Well, those will cancel. And then minus c over d squared times 1/2 is just 1 minus 1/2 times c over d squared, or c over 2d squared. And that's the spring constant. And the units of this make sense because we see that the c, that was an energy function, and we already said that c was an energy, or Newton meters, that is joules, and that the spring constant is in Newton meters divided by meters squared, which is a Newton per meter, which is the right units for spring constant. Always reassuring. And that concludes our discussion of energy landscapes to understand bond properties.